Morning everyone. So I'm going to talk about using flammable refrigerants safely, something that we've covered many times in the past. So the outline is to talk first of all about flammability, identify the hazards in the flammable refrigerants, and then look at which refrigerants are flammable and where they're used, and we're splitting those into the A2Ls and the A3s. Look at the hazards in more detail, and then more importantly how you work safely on site, and also look at the application side. So there are obviously with flammables maximum charge sizes, and there are some other restrictions as well. So I'll be looking at that too. But just to note that this is not a full flammables training program, okay? This is just a 20-minute talk capturing the most important points. So I'm going to start by looking at flammability, and that leads on to safety classification to explain the difference between A3s and A2Ls. So in order to get combustion, you need three things shown by the fuel triangle. So you need something flammable, like the flammable refrigerant. That has to be mixed with oxygen, which is obviously in the air. And if you get the right mix of air and refrigerant, then you need a source of ignition to actually get combustion. That mixture of air and refrigerant is different for the A3s, like the hydrocarbons, and the A2Ls. So for the A3s, you need less refrigerant to start to become flammable, so around about 2% of refrigerant in air, whereas for the A2Ls, you need more refrigerant to become flammable. So for R32, for example, a very widely used A2L refrigerant, you need 14% to start to become flammable, to become into this range here where you're flammable. So looking at the differences between A3s and A2Ls in a bit more detail, I guess we should start with the A1s. A1 or B1 refrigerants are totally non-flammable. So that's things like with A1 refrigerants like CO2, 404A, 134A, etc. And then we go up in degree of flammability. So really what I want to do here is just to describe the difference between an A2L and an A3. So the A3 refrigerants are higher flammability, and this is things like the hydrocarbons. In order to be in that category, the lower flammability level, in other words, percentage in air by volume, needs to be less than or equal to 3.5%. So very little refrigerant in air to get you into an A3 category. Whereas with the 2L category, the lower flammability category, you need more than 3.5% of refrigerant in air. And then in addition to that, the actual heat produced with a higher flammability refrigerant with an A3 will be greater than it would be with the A2L refrigerants. So you will get less heat produced by a 2L refrigerant should you reach combustion. And then the third thing is the flame propagation. The flame propagation is very fast with the A3s and is much slower, round about walking pace, with the A2Ls. So basically the A2Ls are more difficult to ignite, and when they are ignited, the effect of combustion is less. So looking at sources of ignition, a naked flame will definitely ignite A3s and A2L refrigerants, no doubt about that. So that's things like matches, cigarette lighters, brazing torches, etc. Electrical switches will probably ignite an A3 refrigerant, but is unlikely to ignite an A2L, although we can't say absolutely impossible. But of course, there are electrical devices that are EX rated, which means they've been designed and tested to a specific standard. And if they are EX rated, then they will never be sources of ignition for any of the flammable refrigerants. And you know they're EX rated because they'll have the little EX label on them somewhere. From a service point of view, one of the really important points is that if you've got an EX rated component that you're changing, you must change it like for like. So looking at the flammable refrigerants in more detail, starting with the hydrocarbons, I'm only going to talk about these really in outline because Chris is going to talk more about the hydrocarbons, but you've got three that we predominantly use. Isobutane at R600A is used very widely in domestic refrigerators now. It's really only the American ones that don't use R600A, but also used in some small commercial integral type systems. 290 is propane and 1270 is propene or propylene. They're used in larger commercial systems such as integrals, but also chillers, and other small systems. But as I said, Chris is going to talk more about the hydrocarbons. The A2Ls, there are a lot of them now. The predominant ones I've put in bold here. So R32 is very widely used. It's an HFC, but it's unusual because it's a flammable HFC, and it is widely used now in split air conditioning, but also VRV, VRF type systems as well, possibly in some refrigeration applications. 1234ZE and YF are both HFOs. I'll explain what that means later on, but they're used in things like fluid chillers, car air conditioning, and some other stationary systems. And then we've got a whole range of A2L blends. The most commonly used at the moment are the 454A and C. And they have been used in things like medium to large retail, in condensing unit systems, in some cold stores, and in food processing. And in general, the A2Ls fit between the hydrocarbons and CO2. So hydrocarbons are used in very small systems and should continue to be used in small systems. There's no reason to replace those with A2Ls. And CO2, of course, is used in very large systems. And the A2Ls really fit in that gap in the middle. So looking at some of the A2Ls in more detail, R32 is used now in most new split systems. It's starting to be used in larger systems. The pressures and temperatures are very similar to 410A, so it looks like 410A. But of course, there are important differences such as flammability. It does have slightly better energy efficiency than 410A. Unlike some of the other flammables, it comes under the F-gas regulation. It's got a reasonably high global warming potential, so you couldn't really say that it's a totally long-term refrigerant. And it's important that you don't retrofit R32 into a 410A system, or the other way around. Then we've got these newish refrigerants, 1234ZE and YF. They're HFOs, and basically HFO stands for hydrofluoroolefin. So it is an HFC, but by a different name, really to differentiate it from the very high global warming potential HFCs, because the GWP of the HFOs is very low, almost as good as the hydrocarbons. We mainly use the HFOs in blends, so they're used in a lot of the A2L blends. So we have a lot of these, and they can include the HFOs, but as well as that, some of the blends have CO2 in, have other HFCs in, and hydrocarbons. One example is 454C, which is being used in some retail applications, and that's a mix of R32 and 1234YF. If you want to know what refrigerants are, A2Ls, and also other information about them, then you need to look at the data sheet, or EN 378. Part 1 has a very long table of different refrigerants with different aspects of the refrigerant within there. And that table is shortly to be taken out of part 1 and put as a separate part to EN 378 because it needs to be updated very, very frequently. So looking at the hazards, obviously we're going to talk about flammability, but the other hazards as well. So flammability is the main hazard. There's an explosion risk as well, of course, if accumulated refrigerant gathers in a confined space and is then ignited. And of course, what we do during service is avoid that risk through good service procedures, which I'll touch on in a minute. And also from a design point of view, we limit charge so that this actually can't happen. Liquid burns and asphyxiation exactly the same as the other refrigerants. And then the A2Ls also have this possibility of hydrogen fluoride formation, like the other HFCs, but it's perhaps more likely with something that you can actually burn. This happens because a burnt HFC or a burnt HFO forms hydrogen fluoride. When that is mixed with moisture, for example, in your lungs, that forms hydrofluoric acid, and that's what makes you choke. It's highly toxic. And if you're affected by that, you need to make sure that you move into fresh air immediately, and you may well need medical attention. So that brings us on to working safely with the refrigerants. I'm going to just touch on this in outline. As I said, this isn't a full training session, but this covers the most important points. One is your work area. That needs to be safe. So you've normally got a 3-meter zone around you that's free from sources of ignition. It's going to be well ventilated. If you're working with hydrocarbons, you're going to have flammable gas detection in there, and you're going to have a fire extinguisher. Your leak test method needs to be safe and sensitive, so it needs to be the correct leak detector for the refrigerant. The recovery machine needs to be a safe recovery machine suitable for flammable refrigerants, and also need to make sure that you don't overfill cylinders, especially with hydrocarbons, which are very low density. The evacuation process needs to be safe, so you need to avoid the source of ignition which may be present on the vac pump by plugging it in and controlling it remotely from your work area. You need to make sure you've safely removed hydrocarbons and the other flammable refrigerants prior to unbrazing, and then backfill with nitrogen. I'm going to touch on that in a minute. Make sure the charge is accurate. Lots of these flammable refrigerants have a lower charge, so accuracy is more important. And then if you're replacing components, just make sure that you're replacing like for like, especially electrical components. When you're working with A2Ls, you need to follow the same procedures as you would do with hydrocarbons, but just you can't vent A2Ls because they're mostly HFC type refrigerants. There's a lot of A2L specific equipment out there now, so there's no reason why you need to work with anything other than A2L specific equipment. If you are unbrazing a system, then you need to make sure that all the flammable refrigerant is out of the system before you do that. So the system needs to be recovered until it's under a vacuum. Then that vacuum needs to be broken with nitrogen. So you're backfilling with nitrogen to a very small positive pressure, maybe 0.1, 0.2 of a bar above atmospheric pressure. Then it's safe to either cut or unbraze the system. And rebrazing, we would recommend that you purge nitrogen through the system, obviously making sure that there's one point open to atmosphere to allow you to purge the nitrogen through. And as I said earlier, specifically with R32 systems, but with all refrigerant systems, don't retrofit a non-flammable system with a flammable refrigerant. So that leads us on to talking about the application side in a little bit more detail. And we're going to look at system design and maximum charge sizes. We obviously design flammable refrigerants to avoid the issue of flammability in the event of a leak. So this is what we're aiming to do here. There are a number of standards that cover this. So standards are there to make sure that systems are designed safely. There are standards that cover products specifically, and I think Chris will probably talk about this in a little bit more detail, but they're there specifically for small charge systems like integrals, and also for air conditioning systems and heat pumps. So where a product standard exists for your particular system, that's what should be followed. Where a product standard doesn't exist, then there's a general standard EN 378. That you would need to follow. These standards are very up to date now with regard to flammable refrigerants, so the design of flammable refrigerant systems is covered very comprehensively in them. In general, what we do with flammable systems, or what the standards do, is we limit charge size. Now that charge size is higher for A2L refrigerants than it is for hydrocarbons, just to reflect the different degrees of flammability. So a typical upper cap for an A2L system in a supermarket, for example, would be somewhere between 55 and 80 kilograms, depending on the lower flammability level of the refrigerant. For hydrocarbons, for example, the upper cap in a typical supermarket shop floor would be about 1.5 kilograms. So there is obviously quite a difference there. The actual limit could well be lower than that, though, because of room size and the actual application. And in order to allow that sort of charge size with A2Ls, there may well be some construction requirements. There are actually 13 equipment requirements to ensure, for example, enhanced tightness to allow us to use larger charge sizes of A2Ls. And we may need to take some additional safety measures as well with A2Ls. For example, an alarm, additional ventilation, or safety shut-off in the event of a leak. Other principles that we follow when we're designing flammable refrigerant systems is that we minimize our charge size, for example, by using microbore evaporators and condensers, by making sure that the receiver size is as small as possible, orientating it so that it's vertical rather than horizontal, possibly using it not as a liquid receiver, but as a as a different type of vessel. And then also we use secondary systems much more with flammable refrigerants rather than primary systems to reduce the charge size. There'll also be some differences in electrical devices, especially on hydrocarbon systems. And again, that's something Chris will talk about. And also we may well be ventilating systems permanently, so things like condenser fans might be running all the time. So to give you some examples of hydrocarbon, one main example of an application of hydrocarbons in large supermarkets, this is a typical Waitrose supermarket where hydrocarbons are being used in integrals on the shop floor. Typically, the charge in each of these little condensing units here is about 1 kilogram, maybe less, and they are water cooled rather than air cooled. So chilled water is circulated around the shop floor to take the heat away from the water cooled condensers in these little condensing units. And then that water is chilled with externally mounted chillers. And the charge size in these chillers could be 7.5 kilos per circuit. They're outdoor mounted, so actually in many cases the charge size is actually not limited by the standards. And then you've also got small monoblock systems running the cauldrons. Their charge size in these is typically going to be about 200 grams. That's limited by the size of the actual cauldron, so that we don't exceed the about 20% of the practical limit in the cauldron. With A2L condensing unit systems, again for a shop floor, this particular example is 454C. These numbers here, these maximum charge sizes here, change very slightly with lower flammability level. So this is specifically for this particular refrigerant. It's covered by EN 378, access category A, which means it's a public area. So the charge size is limited by the room size. When we go to, if we're below this level here, in this case 11.4 kilograms, it's limited by the room volume. If we want to go above that charge size, and we could go up to 57 kilograms with this particular refrigerant, then we have to observe the construction requirements. For example, that covers how we join pipe and components, and we may need up to 2 additional safety measures. So we may need gas detection coupled to an alarm and coupled to something like refrigerant shutdown. And then when we look at air conditioning applications, the standard is different. So we're looking at a different standard here. So a typical comfort cooling application, our charge size is again limited by the room size, a slightly more complicated equation here, but it gives us a maximum room size, a maximum charge dependent on room size, up to 16 kilograms. If we want to go above that, then the additional measures that we would have to take really don't make sense for something like a split air conditioning system. You don't need to do that calculation because the manufacturers of the air conditioning system will have done that for you. So for a given refrigerant charge, you have got a minimum room size that system can be used in. So summarising this particular presentation before we go on to Chris's, we are using flammable refrigerants already very widely. We've been using flammables in the UK since the mid-90s. So we are very experienced at that in the UK. That of course has been hydrocarbons. There really isn't any need to use A2Ls where we are already successfully using hydrocarbons. What the A2Ls allow us to do is to expand our use of flammables into larger systems. We are designing those systems to appropriate standards. The standards exist, they're very comprehensive, and they provide maximum charge sizes for applications and also the other things that we need to do to mitigate the risk. There are some new service procedures that you need to follow, but they're very practical. Engineers have been doing that now for several decades quite successfully. There is some new service equipment now available for A2Ls. And because of all that, we've actually adopted hydrocarbons very safely. We've had a successful adoption of hydrocarbons in the UK, and we are following that up with A2Ls as well. And that's really because we're following the standards properly, and engineers are being trained. As a business, Cool Concerns has probably trained 10, 20,000 engineers through the safe handling of hydrocarbons. Thank you very much.